Hello everyone, welcome to 10-Minute Physiology. In today's video, I'm going to try to explain to you how the nicotinic receptor works in synaptic transmission in under 10 minutes. So let's give it a go. So let's start off by looking at a neuron. And what we're going to do is we're going to zoom in on the synaptic terminal of this neuron. Now inside the synaptic terminal, what we're going to see are vesicles. Now the vesicle that we see here is empty, and this vesicle was made in the cell body of the neuron. So what happens is that this vesicle, which we see here, which is empty, is synthesized inside the cell body. Then this empty vesicle is transported down the axon via fast axonal transport mechanisms into the synaptic terminal. Now, once this vesicle reaches the synaptic terminal, this vesicle needs to be packaged with neurotransmitters. Now, in order for this vesicle to be packaged with neurotransmitters, we have to use a couple of different components. So let's take a look and see. So if we zoom in inside the cytosol of the synaptic terminal, what you would see is that there are plenty of mitochondria. Now, as you may know from your undergraduate classes or graduate classes, the mitochondria produce ATP. Now, ATP in this case will be used by the vesicle in order to transport acetylcholine into the vesicle. So how is the vesicle going to do this? Well, the vesicle is going to use two different transport proteins. The first protein is called a VATPase. Now, the VATPase is otherwise known as a proton pump. So what it's going to do is it's going to take the ATP produced by the mitochondria, hydrolyze it to ADP and inorganic phosphate, and it will use the energy released by that hydrolysis in order to pump protons into the lumen of the vesicle against the concentration gradient. Now, because this VATPase is producing a proton gradient, another protein can use this proton gradient in order to package acetylcholine into the vesicle. Now this is going to be a proton acetylcholine exchanger, which we see right here in the vesicle. So what's going to happen is that protons will move down their concentration gradient from the inside of the vesicle to the cytosol, and this will be used in order to package acetylcholine from the cytosol into the vesicle. So in this case, acetylcholine is being packaged into the vesicle by using the energy released by protons being moved down their concentration gradient. Now, this acetylcholine doesn't just come from nowhere, doesn't just pop out of nowhere. So what's going to happen is that this acetylcholine has to be synthesized, and it's going to be synthesized from two constituent parts. They are going to be acetyl coenzyme A and choline. Now, these two reactants are going to react together to form acetylcholine by using a specific enzyme called choline acetyltransferase. So this is how acetylcholine is going to be packaged into the vesicles. Now, how is this acetylcholine going to be released? Now, if you watched my previous video on the introduction to synaptic transmission, you should have a pretty good idea of this. But for those of you who didn't watch it, here's a quick reminder. So what we see is that we have our vesicle now packaged with acetylcholine, and the acetylcholine packaged vesicle will now go to a specific region of the synaptic terminal called the active zone, where it will be awaiting to be released. So what's going to happen is that an action potential will be propagating down the axon, and it will cause the opening of voltage-gated sodium channels. The sodium will move into the axon, and the sodium will depolarize the cell membrane. And the cell membrane, when it depolarizes, will open voltage-gated calcium channels. The voltage-gated calcium channels will allow calcium to flow in, which will increase the intracellular calcium level, which will then facilitate the fusion of the vesicle to the plasma membrane of the synaptic terminal, releasing acetylcholine. Now, what's going to happen when acetylcholine is released into the synapse? Now, when acetylcholine is released into the synapse, what's going to happen is that on the target cell, there is going to be a specific receptor called the nicotinic receptor. Now, as you can see here, the nicotinic receptor is a pentamer. So in other words, it has 5 different subunits. Now, inside the nicotinic receptor are 2 binding sites, and these 2 binding sites both bind to acetylcholine. So acetylcholine will bind to the first binding site, and then another acetylcholine will bind to the second binding site. Now, when this happens, when both acetylcholines bind to the nicotinic receptor, what's going to happen is that the nicotinic receptor will open. Now, the nicotinic receptor is a ligand-gated ion channel, and this means that when a ligand binds to this channel, it will cause the channel to open and allow ions to pass through. So what ions will pass through this channel? And how will they pass through? Will they move into the cell or out of the cell? Well, what this depends upon, first of all, is the membrane potential. So let's first assume that the membrane potential is negative. So we're at the resting potential. Remember that the resting potential is around negative 70 millivolts. So what's going to happen in this case is that you're going to basically have 3 different ions passing through the open channel. The first ion is going to be sodium, and when this channel is open, sodium will flow down its electrochemical gradient from the outside of the cell to the inside of the cell. The second ion is going to be calcium, and calcium will also flow down its electrochemical gradient from the outside of the cell to the inside of the cell. Now the third ion is going to be potassium. Now potassium will move down its electrochemical gradient from the inside of the cell to the outside of the cell. So what is the net effect of this channel? Well, the net effect depends upon the permeability of each ion to the nicotinic receptor. And what so happens to be is that the sodium ion has the greatest permeability, followed by the calcium, and then followed by the potassium. So in other words, you're going to have much more sodium passing through this receptor than potassium passing through. So the net effect of the nicotinic receptor opening in a hyperpolarized state or at a negative membrane potential is that it will cause the cell to depolarize. Now, you may remember that I specified what the membrane potential was of the cell before we talked about the effects of the nicotinic receptor opening. Now, in order to understand this, I have a diagram here. And this diagram is basically telling you how the current passing through this receptor will vary at different membrane potentials. Now, what we see is the following. We see that when the membrane potential is negative, which we see right here, so when the membrane potential is negative, the current is negative. So in other words, when the membrane potential is negative or below 0 millivolts, the current is negative, and this means that current will move into the cell. Now remember that current is the movement of positive charge. So when current is negative, this means positive charge is moving into the cell, and the cell is depolarizing. It's when the nicotinic receptor is open. Now, when you look at a positive membrane potential, which we see right here, you'll see the opposite effect, that the current is positive. So when the membrane potential is above 0 millivolts, the current will be positive, which means positive charge is moving out of the cell, which will therefore cause the cell membrane potential to hyperpolarize or become more negatively charged when this receptor is open. So an important point to point out on this graph is this point. And this point passing through the origin is called the reversal potential. And the reversal potential, or the reversal voltage, is the membrane potential at which the net current is 0 through this open receptor. So in other words, when the membrane potential is 0, this is the reversal potential of the nicotinic receptor, which means that the net inward current will be equal to the net outward current, which means that no net current is being passed. So the reversal potential for the nicotinic receptor is 0 millivolts. So let's apply this idea now to the cell. So if we bring back our cell with our nicotinic receptor, and we have our acetylcholine, the acetylcholine will bind to the nicotinic receptor at the 2 binding sites, which will then cause the nicotinic receptor to open. When this happens at a negative membrane potential, so at rest or at any hyperpolarized membrane potential, what is going to happen is that you're going to have a net inward current, which means positive charges entering into the cell, and this would cause the cell to depolarize. Now, what if we were to change the membrane potential to a positive membrane potential? So when the membrane potential is positive, when this receptor is open, what's going to happen is that the current will now be moving out of the cell. So in other words, positive charge is now leaving the cell, which would therefore cause the cell membrane potential to hyperpolarize or become more negatively charged. So let's summarize what we talked about in this video. So in this video, we showed that acetylcholine is packaged into vesicles using secondary active transport. And we saw that the nicotinic receptor has two binding sites for acetylcholine. And the nicotinic receptor, when it's opened, will allow sodium and calcium to move into the cell and potassium to move out of the cell. Now, we also saw that when the target cell is depolarized, so above 0 millivolts, the nicotinic receptor facilitates a hyperpolarizing outward current. And when the target cell is hyperpolarized, so below 0 millivolts, the nicotinic receptor facilitates a depolarizing inward current. So I hope you enjoyed this video, and I hope to see you in the next one.